Hey there, imagine a particle so tiny, it's smaller than anything you've ever seen. Now imagine it doing something impossible, moving forward in time and backward in time, and somehow still obeying the rules of the universe. Sounds crazy, right? Sounds like science fiction. But it's not. This is real. This is quantum mechanics. And I'm going to take you inside one of the strangest puzzles I ever faced, a time paradox in particle physics that had even the smartest scientists scratching their heads. Stick with me, because by the end of this video, you'll see the universe in a whole new way. You'll understand a problem that once seemed unsolvable, and you'll learn the way I think. Curious, playful, visual, the way a physics genius approaches the unknown. Welcome to Feynman Flux, and go ahead, hit that subscribe button because the adventure's just beginning. Now let me tell you something most people don't know about me. People think physicists are all suits, serious faces and chalk dust. Not me. I played the bongos, I cracked safes, I drew cartoons to explain physics. My curiosity didn't come from lectures. It came from asking why, about everything. Spinning plates, bouncing balls, even light itself. And then there was the time paradox. Particles interacting in ways that seemed impossible, like they were influencing their own past. Now, if you're thinking, that can't happen, you're right, by classical rules, but quantum mechanics laughs at classical rules. The equations existed, the experiments existed, but something didn't add up. Scientists were stuck. They couldn't see the problem clearly. Here's what I did. I stopped worrying about being right or proving anyone wrong. I asked simple questions. I visualized the particles as little stories. I drew lines, arrows, little diagrams showing how particles split, merged, and danced through time. Suddenly, what seemed impossible became clear. These weren't just drawings, they were tools. My secret weapon. What the world would later call Feynman diagrams. And they changed everything. They showed exactly how particles exchanged energy, how time could appear to bend in these tiny worlds, and how quantum electrodynamics could finally make sense. Some of my earliest diagrams were on the backs of envelopes at dinner parties. I literally played with the universe while everyone else was finishing dessert. That's curiosity for you. It doesn't punch a clock. It shows up anywhere. Solving this paradox, well, it led to the Nobel Prize in 1965, along with Julian Schwinger and Shinichiro Tomonaga. But here's the secret most people don't know. The prize wasn't just for diagrams. It was for a new way of thinking. Curiosity-driven science. Seeing the invisible. Making sense of the impossible. That's what really mattered. Now here's what I want you to take away. Curiosity isn't just asking questions. It's seeing differently. It's drawing lines when others see only numbers. It's asking what if, and being brave enough to play with ideas. That's how I solve the time paradox. That's how you can tackle problems in your own life, big or small. Ask simple questions. Visualize the problem. Never stop learning. And remember, even the smallest insight, a doodle on a napkin, a crazy thought, can solve a puzzle that stumped the best minds. By now, you're probably wondering, can I really think like Feynman? Can I tackle the impossible? The answer is yes. You just need curiosity and imagination. That's what Feynman Flux is about. Exploring the universe not as a boring set of equations, but as a playground full of puzzles, surprises, and stories waiting to be told. So here's my invitation. Subscribe, stay curious, and get ready. In this video, you're going to see exactly how that strange time paradox unfolded, how I used diagrams to solve it, and how it all led to one of the greatest breakthroughs in 20th century physics. By the end, you'll not only understand the Nobel Prize-winning discovery, you'll understand a way of thinking that makes physics alive, playful, and a little magical. The universe isn't a puzzle to fear. It's a playground to explore. And if you watch closely, you might find that the answers aren't hidden in some far-off equation. They're in the way you ask questions, imagine possibilities, and draw your own lines, connecting the dots. That's how I solved the paradox that stumped the best minds of my time. And that's how you can start thinking like a physics genius, too. So buckle up, open your mind, and welcome to Feynman Flux. One paradox in time, that's all it took to shake the foundations of physics. Imagine a puzzle so strange, so baffling, that even the brightest minds of my generation couldn't make sense of it. And then imagine someone, in this case, me, seeing it differently, seeing a path where no one else could. That's how physics changed forever. That's how curiosity and playfulness, not just intelligence, can crack the universe open. I wasn't always the physicist people think of. Long before MIT, Princeton, or the Manhattan Project, I was a curious kid in Far Rockaway, New York, taking apart radios just to see how they worked. Most kids were playing baseball. I was trying to make a wave bounce in a homemade oscilloscope. I'd pull things apart, figure out how they ticked, and then put them back together, sometimes in better shape than before. And I was mischievous about it too. I once made a makeshift alarm clock that would ring every 5 minutes just to annoy my brother. And in the process, I learned about circuits and timing. That's where my love for problem solving began, not in a classroom, but in a room full of curiosity. By the time I got to MIT, I wasn't just memorizing equations. I was questioning them. I wanted to understand the why behind every formula, not just the how. That curiosity took me to Princeton for graduate work and eventually to Los Alamos working on the Manhattan Project. But even in the midst of bombs and secrecy, I kept my sense of play. I'd sketch diagrams on whatever scrap of paper I could find, turning the most serious physics problems into puzzles, sometimes even games. And it was exactly that playful curiosity that let me tackle a problem most physicists thought unsolvable, a time paradox in quantum electrodynamics. Quantum mechanics is strange enough on its own. Particles behaving like waves, waves behaving like particles, energy popping in and out of existence. But then comes this one riddle, the time paradox. It's the kind of thing that makes you pause and wonder, does time really behave the way we think it does? Physicists were wrestling with interactions between particles, electrons and photons, where conventional mathematics seemed to break down. Equations would give contradictory results, predictions that didn't match experiments. It was like trying to map a landscape that changed every time you blinked. And that's when I decided to try something different. Most physicists were buried in formulas, trying to wrestle the paradox into submission. I thought, why not see it? Why not draw it? My approach wasn't about proving anyone wrong. It was about understanding, visualizing, and playing with the problem until it made sense. And that's how Feynman diagrams were born. Picture this: electrons moving through space, photons hopping between them, interactions happening forward in time and backward in time, in a tangle of equations. It's hopeless. On paper, it's chaos. But draw a line for each particle, arrows for direction, wavy lines for photons. Suddenly, the interactions are a story. Suddenly, the impossible becomes clear. You can track each exchange, each interaction, each path, and the math follows naturally. It's visual, intuitive, and yes, even fun. I remember sketching one of my early diagrams on the back of an envelope at a dinner party just to see if it worked. My friends thought I was doodling. I was rewriting the rules of physics. These diagrams weren't just a trick. They were a breakthrough in understanding quantum electrodynamics, the theory describing how light and matter interact. Suddenly, physicists could calculate probabilities of particle interactions accurately, predict outcomes that had puzzled experiments for decades, and visualized processes that seemed invisible. It simplified what had seemed overwhelmingly complex and opened the door for a generation of discoveries in particle physics. And perhaps most importantly, it showed that curiosity-driven thinking, combined with playfulness and imagination, could solve problems that raw intelligence alone couldn't touch. Here's a story most people don't know. When I first presented these ideas, some senior physicists were skeptical. They didn't trust that simple lines and arrows could replace complex integrals. One professor said, "You're drawing cartoons, Feynman. Physics isn't cartoons." And I said, "Exactly. But watch what they do." Within a few years, these cartoons were transforming research. They were in textbooks. They were tools in labs. They became the language of particle physics. And for that work in 1965, I was awarded the Nobel Prize in Physics along with Julian Schwinger and Shinichiro Tomonaga. But the real prize wasn't the medal. It was the proof that seeing the world differently, being playful, curious, and unafraid to challenge conventional methods could change everything. And that's the real magic, because the world doesn't always reward cleverness alone. It rewards curiosity, the kind that starts in a kid's bedroom, taking apart radios. It rewards the courage to question, to doodle diagrams on envelopes, to see stories where others see numbers. That's how the time paradox was solved. That's how a single mind willing to play transformed quantum physics. I want you to picture this: a particle moving through time forward, backward, colliding, exchanging energy, changing the universe in a tiny but measurable way. And now imagine understanding it, not just with equations, but with your eyes, your mind, your imagination. That's the power of Feynman diagrams. That's the power of curiosity-driven science. It's not about memorizing formulas. It's about thinking differently, about breaking down impossible problems into simple visual steps. Here's another little-known fact. I love to teach, but I hated rote lectures. I wanted students to feel physics, to touch it, to see it. Sometimes I'd bring in popsicle sticks, bongo drums, or even candy to explain quantum ideas. Why? Because the human mind understands patterns, visuals, and stories, and quantum electrodynamics, with all its paradoxes and puzzles, is just a series of patterns waiting to be discovered. That's what I want you to see too, that these ideas, as mind-bending as they are, aren't beyond anyone's reach if you approach them with curiosity and playfulness. And it doesn't stop at theory. These breakthroughs changed real-world physics. Particle accelerators, quantum computing, experiments at CERN, all of it rests on understanding interactions that once seemed impossible. Every new particle discovered, every quantum effect calculated, builds on the insights from the time paradox and the diagrams I drew. Physics isn't just abstract math, it's a living, breathing exploration of the universe. And anyone with curiosity, imagination, and the courage to ask simple questions can be part of it. So what's the secret? How did I, Richard Feynman, approach a paradox that others couldn't solve? Curiosity first, playfulness always. Visual thinking. Asking questions no one else thought to ask. Sketching, imagining, experimenting, failing, and trying again. The Nobel Prize was just a recognition. The real reward was understanding something no one else could see and having the joy of discovery along the way. And now, as you watch this, I want you to feel that same joy. Think about problems differently. Break them into parts. Draw them, doodle them, play with them. Physics, mathematics, even everyday life. It's all a puzzle, and the answers are always waiting for a curious mind. That's how the quantum riddle was solved. That's how it changed everything. And that's the way curiosity and imagination can change your world too. A paradox in time, a genius mind. One Nobel Prize winning solution. Sounds like the start of a science fiction story, right? But it's not. This is real physics, real history, and yes, real me, Richard Feynman. I wasn't born thinking about Nobel Prizes or quantum mechanics. I was a kid in Far Rockaway, New York, curious about everything. Radios, watches, locks, you name it. I wanted to know how it worked. I'd take things apart and sometimes put them back together, sometimes not. I remember my brother getting frustrated because I'd rig a bicycle bell to go off every few minutes, just to test the timing. That's the kind of tinkering that shapes a curious mind. It's the kind of curiosity that eventually leads to Nobel Prize-winning discoveries.
Curiosity was my first tool, playfulness, my second. MIT was the next stage, but even there, I wasn't just memorizing equations. I wanted to see the rules behind them. I wanted to understand the world, not just recite it. That same curiosity drove me to Princeton for graduate studies and later to Los Alamos, working on the Manhattan Project. I was surrounded by the smartest minds of my generation, yet I never lost my playful approach. While others buried themselves in serious math, I drew diagrams on scraps of paper, imagined particles as characters, and approached physics like a puzzle to play with.
Then came the paradox, the kind of problem that stops the world in its tracks. Particle physics had advanced tremendously, but there was this one riddle, a time paradox in quantum electrodynamics. Electrons are interacting with photons in ways that seemed impossible. Trying to calculate it with conventional methods, a nightmare. Predictions didn't match experiments, equations contradicted themselves. Scientists were stuck. It was like trying to predict the behavior of a storm that moves backward and forward at the same time. Impossible. I remember staring at it and thinking, well, if we can't solve it the usual way, maybe we need a different way to see it. That's when the solution hit me. Not in a lecture, not in a formal meeting, but in sketches, doodles, and imagination. Lines for particles, wavy lines for photons, arrows showing the direction of time. Suddenly the chaos became a story, a narrative, something human, something visual. That's how Feynman diagrams were born. Feynman diagrams are deceptively simple, but their simplicity hides their power. They allow you to visualize particle interactions across time, to see how electrons and photons collide, exchange energy, and influence each other, even in ways that seem to defy classical intuition. Before these diagrams, quantum electrodynamics was an intimidating, nearly impossible landscape of complex math. After it was navigable, suddenly physicists could calculate probabilities, predict outcomes, and understand interactions that had baffled the best minds for decades. I'll share a little secret. Some of my first diagrams were drawn on the backs of envelopes during dinner parties. People thought I was just doodling. I was rewriting the rules of physics. Those doodles transformed an entire field. And that's the magic of curiosity-driven science. A playful mind sees patterns where others see confusion. And the impact, tremendous. These diagrams became standard tools in particle physics. They appeared in textbooks. They shaped experiments. They helped physicists understand the most fundamental interactions in the universe. And in 1965, they led to the Nobel Prize in Physics, awarded to me along with Julian Schwinger and Shinichiro Tomonaga. But let me be clear, the Nobel Prize wasn't the goal. The goal was understanding, seeing the invisible, making sense of the impossible. That's the real achievement. You might wonder, why did no one else see it? Why hadn't these diagrams been invented before? It required a combination of curiosity, imagination, and fearlessness. Most physicists were trained to follow equations, to work within the confines of conventional methods. I was trained to question everything, to play with ideas, and to visualize what others considered unseeable. That's why I could see the solution where others saw a wall. Let's go back a little. My early life was full of experiments that shaped this mindset. As a boy, I once built a small motor from scratch. It didn't work at first. I tried different coils, magnets, wires, and arrangements. I failed dozens of times. And then one day, it ran perfectly. That moment, the joy of discovery through trial, error, and imagination, is exactly how I approached quantum electrodynamics. Break it apart, play with it, and eventually the solution reveals itself. And that's what made the time paradox solvable. Imagine trying to predict something that defies time itself. Classical intuition fails, equations fail, but a visual approach, a playful approach, that works. A diagram tells the story. Electrons move, photons interact, possibilities unfold, and the math falls into place naturally. It's elegant, it's powerful, and it's accessible. Here's another anecdote. During my Manhattan Project days, I was working on bomb calculations, serious life or death work. But I kept thinking about these diagrams. On breaks, I'd sketch interactions, sometimes even on scraps of lab notes. Some colleagues thought I was wasting time. But physics is never wasted when curiosity drives it. It's never wasted when imagination guides it. And that playful mindset is what led to a breakthrough that changed the entire field of quantum mechanics.
The legacy of these diagrams is massive. They didn't just solve a paradox. They transformed physics culture. Students began to learn physics visually. Experiments became clearer. Calculations became simpler. Research accelerated. And all of it started from curiosity, observation, and the courage to see differently. It's a reminder that genius isn't just about raw intellect. It's about how you approach a problem. It's about curiosity, imagination, and a willingness to play with the universe.
I want you to see this humanly. Physics is not just numbers on a page. It's a story unfolding, a drama of particles, energy, and time itself. And with curiosity as your guide, you can follow that story. That's what I mean by learning physics like Feynman. Ask simple questions, draw the patterns, imagine the interactions, play with the problem until it starts to make sense. That's the mindset that solved the time paradox. That's the mindset that led to a Nobel Prize. Even today, Feynman diagrams are everywhere, from particle accelerators to quantum computing. They guide the understanding of everything from the tiniest quark to the most complex interactions of light and matter, and the principles behind them. Curiosity, visualization, playful experimentation remain timeless. The paradox may be solved, the Nobel Prize awarded, but the mindset that solved it is alive in every curious mind willing to ask, what if? Don't forget the human side. I was never a perfect student. I broke the rules, I played drums, I told jokes, I cracked safes, but every bit of curiosity, every experiment, every playful idea fed into my ability to see what others couldn't. Genius isn't just about intelligence, it's about curiosity. Applied fearlessly, relentlessly, and playfully. That's what allowed me to take a problem that defied time itself and turn it into a diagram, a story, a solution that changed the world. Think about it this way. Every time you see a particle interaction diagram, a textbook page, or a quantum calculation, know that it began with curiosity, a doodle, a question, a refusal to accept that the problem was impossible. That's what I want you to feel. That's the lesson hidden in every Feynman diagram. Curiosity isn't optional. It's the key to solving problems that seem beyond reach. So when you encounter a problem in physics, in math, in life, don't panic. Don't assume it's impossible. Step back, visualize, imagine, break it down, play with it. That's how I approach quantum electrodynamics. That's how I solve a paradox that defied time itself. And that's how you can start thinking like a physicist, like a problem solver, like Feynman. And here's the final thing. The joy isn't in the Nobel Prize. The joy is in discovery, in seeing something no one else sees, in the thrill of connecting the dots, visualizing the invisible, and making sense of the impossible. That's physics. That's curiosity. That's life. And that's exactly what I want you to experience as we dive deeper into the universe of quantum mechanics. Every particle, every interaction, every paradox is a story. And with curiosity as your guide, imagination as your tool, and playfulness as your method, you can read that story. You can solve riddles that once seemed unsolvable. You can see the world differently, and you can, in your own way, become a little like me. Think about the first time you built something. The first time you asked, why? That spark, that's the start of discovery. That's the same spark that led to Feynman diagrams. That's the spark that solved the time paradox and earned a Nobel Prize. And that spark lives in everyone willing to ask questions, to play, to explore, to imagine. Physics is a playground. Quantum mechanics is a playground. And curiosity is your ticket in. Draw the lines. Sketch the interactions. Ask the questions others won't ask. See the story in the chaos. That's the mindset that turns paradoxes into discoveries, questions into answers, and doodles into Nobel Prizes. So take a breath, open your mind, get curious, play with the impossible. And remember, the universe is waiting for your imagination, for your questions, for your diagrams. Think like a physicist, explore, ask, discover, just like Feynman. And that's the story of how a single time paradox led Richard Feynman to reshape physics and earn a Nobel Prize. From his playful curiosity to his genius in quantum mechanics, Feynman showed us that the universe can be understood with imagination, simple thinking, and relentless questioning. If today's dive into Feynman physics and the wonders of science inspired you, make sure to like this video, drop a comment with your favorite Feynman idea, and subscribe to Feynman Flux for more mind-expanding stories. Don't stop here. Click on another video and let your curiosity run wild, because the adventure of science never ends.